Okay. Hi everyone. Can you see me at least a little bit?
Yeah.
You'll have to speak up if you want to ask questions or something, because I can't hear you.
We need to come from here.
Yeah. So I have a picture there as an apology for not being there. This is a picture out of my office window to give you an idea of Adelaide. It's a lovely place. It's a long way away. So unfortunately, the university decided that I wasn't allowed to travel to Brussels, but it saved me a very, very long trip. You can see roughly how long Google thinks it will take me to get to Brussels. Actually, it's a little bit worse because I can't get a direct flight that does that. So from my point of view, it's actually a little bit easier to give the talk from here. But you know, it's a bit disappointing not to get to see you guys in person. Let me get started with the actual talk. Okay, can everyone see the slide?
Yeah.
Yep. Okay. So I've called the talk "Lies, Damn Lies, and Internet Measurement." There's a reason for that. There's a famous quote. Some people attribute the quote to Mark Twain. Other people attribute the quote to Disraeli. It's one of these quotes, I think, that's become so sort of ubiquitous that people are inclined to attribute it to whoever their favorite person is. Nevertheless, it expresses a general sentiment in the public about the role of statistics in many areas of life, and I want to draw some points about network measurement. But I particularly like, I think this cartoon, there's a lot about the role of statisticians in society. I'll get on with my talk though. So, in a group like this, I'm assuming everyone here appreciates the value of network measurements, and that's not an automatic given. Lots of network operators have had to come to that opinion through learning about their own network. So we all appreciate network measurements, but not wanting to overgeneralize. I think there are an awful lot of network operators in particular who don't really appreciate the role of statistics here, or at least they don't really understand a lot of the subtleties. And this can cause a lot of what I believe are quite serious problems. So I have a couple of stories from my times at places like AT&T about the problems that occur because people don't really understand statistics. And the classic one is saying that some X is better than some Y, and this might be network X is better than network Y, or it might be protocol X is better than protocol Y, or it might be network design X is better than network design Y. And often people will want to do things like rank the quality of networks. And often those rankings are just wrong. And I don't want to make it seem like I'm over-dramatizing this, but I have seen cases where people draw conclusions which at the very least are not supported by the data that they have. But in actual fact, I think in many cases they're actually wrong. And this is simply because they did not understand the statistical meaning of the measurements they're taking. The second example that I have from real network operations is even more worrying, and that's, I call it the red board. I've sat there and watched network ops guys looking at a screen full of red lights, red alerts saying things are wrong with their network, and asked them why they weren't doing something about it, and they say, oh, that's red all the time. We don't worry about it. Now, what's the point of a network management system that tells you something that you then just ignore? And why are they ignoring it? And again, this comes down to some statistical subtleties. So what I would do today is try and tell a general story about the role of statistics in network measurement and some of the problems that are out there and how we might do better. By the way, I'm very happy if people ask questions, but you'll probably have to go to someone at the front because the microphone, I probably can't hear what you guys are saying in the back there. So, just to set the scene, a little bit of a history of network measurements. And this is a terribly, terribly crude history of network measurements, and I've missed a huge amount of stuff here, and I apologize deeply for all of the people who feel offended because I haven't mentioned their names here. But what I wanted to do was tell a little bit of a story about network measurements and how they've evolved in our domain. And it goes back to the early ARPANET. And in the early ARPANET, measurements were something that people thought about right at the start, right when they were designing networks. There aren't a lot of these measurements that are actually published, but certainly people look at that. If you look at the literature about how they saw the network and how they improved it, certainly people were looking at measurements of this network. On the other hand, stochastic simulation was a very typical way of approaching network operations or network designs. A lot of the motivation for early network designs was based on simulated models. And at the same time, there was a lot of queuing modeling going on. And there were a lot of stochastic models, particularly for, say, traffic, that were essentially dreamed up. People worked out what sort of characteristics they thought or hoped traffic would have and built stochastic models around them, queuing models and so on. And this motivated a lot of the research that was going on at the time. And of course, these two domains didn't really connect up. A lot of the people who were working on queuing theory, so I did my PhD in queuing theory back in the 90s, and a lot of the people I talked to in queuing theory said, well, now we have this model, how will we use it in a real network? And they couldn't tell me. They couldn't tell me about network measurements that you could use to inform your model. But at the same time, there were various groups, particularly at places like AT&T, and we think about perhaps the Eramili, Leland, Sherman Willinger work on long-range dependence in particular, and Vern Paxson at Berkeley in particular, who in the mid-90s were starting to make real measurements of the early internet, and they were publishing papers about this stuff and publishing data. And so these two communities started to evolve together. And that perhaps reached a culmination around 2000 or a little after, when people started to realize these measurements were actually useful. They were really useful for helping manage and design networks. And so we started to see a whole bunch of conferences. The first one that I know about, the first dedicated conference to network measurement, was PAM. The Passive and Active Measurement was a workshop back then. And we just had PAM 2016 a few weeks ago. Was anyone there? Show of hands. Not too many people, as far as I can see, went along. Anyway, I have to put my little plug in for PAM. I don't think it's been officially announced yet, but the plan is for PAM in 2017 to be in Sydney. So I want you guys to all come to Sydney. It's a beautiful city. It's a wonderful place to have a conference. And I'm sure you'll enjoy it if you do come along. The Internet Measurement Workshop, which later became the Internet Measurement Conference, started in 2001. I don't know when TMA started.
2008.
Does anyone know what year?
2008.
2008, okay. So a little bit later. But there was an explosion of papers on internet measurement around this time. You start to see a lot of papers in internet measurement in other conferences like Infocom and Sitcom as well. Also around the same time, Endace was founded, and as far as I know, Endace is the first company that was dedicated purely to building network measurement infrastructure. I'd love to know if anyone has any counterexamples, any earlier companies dedicated to this problem. But certainly this was a sort of flowering or blooming, and network measurements became much wider, much more widely available. Lots more people were doing it. So this was really good. This is fantastic. It had a negative side though. So a lot of the initial work that was happening, a lot of the the really cool stuff on stochastic modeling of networks seemed to vanish when we had data. Data became the key. Everyone thought data was good. Everything had to be motivated with real data. But data by itself, without a good understanding of what causes the data or a good model for it, is very dangerous. And that's sort of what I want to talk about today. I think that we perhaps went too far to the direction of just thinking data is it. We don't need to worry about anything else. Let's just measure the network and then we'll know everything. We really need to understand it and pick it apart, and that still needs stochastic modeling and statistics. So let me give you a few little examples today, and these are very, very simple examples. They're very potted cartoon examples, but hopefully they illustrate some of the issues that I see underlying network measurement. So without further ado, let's start with a simple example of a test. Now, these come up in all sorts of domains. The classic one that you might imagine is a test for disease in medicine. And this affects almost everyone's life at some point. They will go into a doctor and the doctor will do some sort of test and he'll try and tell you whether or not you have such and such a disease. Now, any test has two sorts of errors. It has false alarms or false positives, and it has false negatives or failures to detect the actual disease. And if you think either of these are perfect in your test, you're probably fooling yourself. Every test has some chance that it will have one or two of these sorts of errors. So a lot of analyses want to try and just talk about one error. They want to talk about the failures to detect or false alarms. But looking at one by itself is always superficial. It lacks depth, and I want to talk about why that is. So let's talk about a little example here. I'm going to posit a simple test, say for cancer or some other nasty disease, and I'm going to say that my test is 90% accurate. So in reality, maybe your test is much better than this, maybe it's worse, but let's just take 90% because it's a nice round number. And I'm going to assume that 1 in 100 people have this disease, which is, it's obviously a ridiculously high prevalence for any sort of serious disease. But these are just nice round numbers for me to do the maths for you really quickly. So imagine you go to your doctor and he tells you in a very serious voice that your test has come back positive. Should you be scared? And this is a question for you. So I want a show of hands about the number of people in the audience. And perhaps the easiest way to say this is that, we have a 90% accurate test. It's 90%, detects 90% of cancers. If you don't have the disease, it's 90% of the time it will tell you don't. How many people think that there's a 90% chance we have the disease? Show of hands. Okay, I've got one hand I can see, maybe a couple. How many people are not worried at all? Okay, not many people have put their hand up for that. Okay. How many people think it might be more like, say, 70 or 80% chance that we have the disease? Not too many hands. You're not committing yourself, you guys. I want to see a little bit more jumping in here. So the question is, should we be scared? So let's do the math here. And the way you would normally do this math is using conditional probability, but I've set up round numbers so that I can do it very, very easily, just straight away on a bit of paper here in front of you. And the way we do it is, let's think about 1,000 people. So this is a sample of 1,000 people representing an average over the population. And I said 1 in 100 has cancer or whatever this disease is. So there are 10 with the disease. Simple calculation on average. And on average, the test will identify 9 out of these 10. So we will pick up 9 of the people who have the disease. On the other hand, I should say we have 990 that don't have the disease. However, the test will say that 1 in 10 of them does because it will generate a false alarm. So actually, it will tell us that 99 people have the disease when they don't. So in total, it will tell us 108 people have the disease. Only 9 of these are correct. So 9 out of 110 is about 9%. So our 90% accurate test actually has a 10% chance of being right. So your doctor coming and telling you you have the disease isn't something to worry about terribly. It's certainly something that you would want to follow up. You might want to have more testing and more diagnosis done, but it isn't something to panic about immediately. Now, I like this example because it has a real-world implication. In reality, these numbers are cooked, but in reality, you see similar tests to this, and doctors don't understand this. Your average doctor out there, presented with that information about the test, would tend to give patients a very scary outlook. And that can have a very negative impact on a lot of people's lives. And so, one of the things that's been a constant problem in health science over the last few decades has been improving the understanding of statistics in doctors and medical researchers. But the same thing applies to us. So let's think of an example from our world. I'm going to imagine that we're looking for anomalies. And for those of you who worked on anomalies, you'll know the idea is a little bit rubbery, but the idea is we're looking for something unusual, and we expect that to have some sort of meaning in terms of problems in the network. So I'm going to propose a test which is even better than my medical test. It's 99% accurate, 99% detection probability, and only 1% false alarm probability. And I'm going to apply this test to standard SNMP link data. So you imagine SNMP, Simple Network Management Protocol. This collects data every 5 minutes, link traffic, bytes, and packets. So let's imagine a moderately large network with 1,000 links. And we'll imagine that we have 10 real problems in our network a day. Now, how many problems does a typical network operator have? Well, that's hugely variable. This is just a number to set the scene. And what I've done there is do a very simple back-of-the-envelope calculation of the average number of false alarms I might expect, given 5-minute data over 1,000 links collected over a 1-day period. And you would expect something like 11,000 false alarms. So in this case, the probability that an alarm is genuine is actually 0.0009. What happens if less than 1% of the alarms you generate actually are a real problem in your network? What happens? The network ops guys, at best, they ignore the alarms. At worst, they just switch the whole system off. Now, that's a 1% false alarm rate. That sounds great. And in fact, I've seen many research papers which talk about a 1% false alarm probability as if it's terrific, wonderful. 1% false alarm rate is still terrible. If you want anomaly detection or network error detection systems to be effective, to be used by network ops people, the false alarm probability has to be tiny. And this is something that very few people seem to understand. There's lots of things you can add on to this, and I don't want to go into too much detail. I have a lot of stuff on this slide, but ultimately it's about the problem of the boy who cried wolf. So the classic, this is a classic fable where the boy goes out and he runs home and says, there's a wolf, and all the villagers turn out to try and get rid of the wolf, but there isn't. And he keeps doing this, and then eventually when there is a wolf, they just say, he always says that, and they leave him to be eaten by the wolf. Okay, so if we have too many false alarms, we're doing exactly the same thing. It's not easy to get false alarm rates that are really low, and it's even harder to measure really low false alarm rates. And we've talked about this in a number of the papers we've written over the years. It's really a tricky problem to do. Any questions? I can't see you guys very well. I'm thinking that no one's got their hand up. Okay, we'll keep going. Second case, second example of a statistical problem that causes some real confusion. It's a thing called Simpsons Paradox. It's called other things as well, but Simpsons Paradox is a pretty common name, and it's one that you can Google if you want to find out more about this. So what is Simpsons Paradox? Well, classic sort of measurement or data that we might look at is some set of percentages, and then we might say A is better than B based on one percentage being bigger than the other. So let me give you an example of that. Back quite a while now ago, Berkeley was sued for gender bias. And the reason they were sued for gender bias was because people studied the admittance rate, and they found out that the admittance rate for male applicants was about 44%, and the admittance rate for female applicants was about 35%. There's a large statistical sample here, so the difference is unlikely to be caused by chance. So this seems, on the face of it, to be obvious evidence that Berkeley was biased. And they were taken to court based on this data. 44% versus 35%. I don't think anyone here would have trouble thinking that that seems like a really important difference. Is it? So now let's have a look at the data broken down by departments. And it's not easy to see everything that's going on here, so I've highlighted it a little bit with some colors just to draw out a couple of parts of this table. So first, let's look up here. This is male applicants for Department A. Male applicants. And you can see there's quite a large proportion of the applicants to Department A were male. And the acceptance rate for Department A was 62%, which is above average. It's quite high for this department, for this university. And likewise, there are quite a large number of male applicants for Department B, which also had quite a high average admittance rate. Now, an interesting thing to look at when you look at this is look at the acceptance rate for women in these two departments, 82% and 68%. There actually seems to be a little bit of bias towards women in those departments. But on the other hand, not that many women applied for these departments. Now, on the other hand, let's have a look at Department E. Department E had 191 male applicants, but 393 female applicants. And its accept rate was 24% for women and 28% for men. Maybe slightly against women, but certainly not significantly against them. Excuse me. But notice there's a lot more women applying for admittance into Department E than men. And when we look at Department F, the story is sort of similar, except there are a similar number of applicants, male and female applicants, but the accept rate for this department is 7%. And it's a much larger relative number of women compared to the total number of applicants. So what's the actual story that's happening here? What's actually going on? Well, a larger proportion of women are applying to a department which has a lower accept rate. So the average over all of these accept rates for women is lower than the average over all of the accept rates for men. When you examine it this way, there is no statistical evidence for bias against women. In fact, if anything, there's a bias towards women in Department A. And so the case was eventually thrown out of court. Luckily, many courts are not all that, many legal systems are not all that statistically sophisticated, but this particular case was thrown out. Okay, so this is a really fascinating phenomenon. On the face of it, it looked obvious. It looked trivially obvious that there was a bias against women. When we examine the details of the data, that bias goes away. And there are lots of instances of this. There are lots of cases where people have looked at very important data sets or data sets that people really care about, and when they tease the data apart, they suddenly find out that a conclusion that they started with is not justified by the data or sometimes completely reversed. And there are cases, for instance, of batting averages in baseball, and also cases of death, people on death row and so on in the US. So this little statistical problem may at one level seem like a mathematical nicety or a little formality, but it has a real impact on people's lives. And it has an impact in our domain. So I'm going to imagine that we're making a set of network measurements of two networks, network A and network B. Who does this? Well, almost everyone out there in this group has probably made network measurements of packet loss at some point or other. But there are also companies that do this. There are companies that go out and they do surveys of different network operators and publish results saying network A had 1% packet loss and network B had 5% packet loss. Back when I worked at AT&T, the company that did this, or the most best-known company that did this, was a company called Keynote. Okay, so obviously network A is better than network B. Everyone happy with that conclusion? Well, let me dig into the details a little bit more. Network X, network A and B have two types of traffic. And again, this is a little bit of a cookbook example just to show you some numbers. But let's imagine there are two types of traffic. One of them, type X, is real time. It's unresponsive to congestion. Because of that, the networks prioritize it. Perhaps it's this sort of video traffic which is being prioritized by the network so that we don't have dropouts. On the other hand, there's a second type of traffic, bulk data traffic. It's adaptive to congestion. And let's assume that both networks have exactly the same amount of congestion. Let's assume both networks drop about 10% of this type of traffic. But the two networks have different mixes of traffic. So I'm going to propose that network A has 90% type X, 10% Y, and network B has 50-50. If we have these proportions, then even though they have exactly the same amount of packet loss for type Y traffic and no packet loss for type X traffic, you get these statistics. You get network A looks like it's got a loss rate overall of 1%, and network B's overall loss rate looks like 5%. So it would be at best confusing to claim that network A is better than network B, given that their underlying properties, their underlying network properties, actually identical. Okay, obviously this is a cooked example. Obviously it's just a toy, it's a cartoon to illustrate the problem. But this is not a particular problem. This is not a problem just with this tiny bit of measurement. This is a problem with the entire strategy of taking some percentages and just comparing them without looking into the details of them. And it's a danger of averages, it's a danger of correlations not implying causality, it's a danger of what we might call confounding variables, or the term I like is lurking variables. And it's that underlying breakdown into different types, different classes, with different underlying percentages that really matters. Okay. Obligatory XKCD cartoon. I love XKCD, so this is one of my favorite little cartoons for them. Let me have a sip of Coke while you guys digest. Okay. Third case study. Estimating loss probability. So we looked at a case where I was estimating loss probabilities. I imagine we'd be sending packets across a network. Again, I'm sure most of the people in the audience have either done this or at the very least read about it in many cases. So I'm not going to make a big deal about it. There are lots of technical issues in doing this well. They're technical issues that have been very well discussed, and I don't want to dwell on them. I want to dwell on the statistical issues here. So imagine we're doing some active measurements. We're going to send n measurement packets across our network. How do we work out the loss rate or the loss probability? Well, we just divide the number of lost packets by the number of packets we sent, the number of measurement packets. Very simple, almost trivial. Okay, and that's right. That's the right thing to do. But there are questions you would like to ask about that measurement. And these come from real questions that people have asked me. And at the time, I had fluffy answers. I have much better answers now, but at the time I could only say a few vague things. It turned out what I said was wrong, unfortunately, and I feel bad about that, but it motivated me to actually go and work out the answers, and I think I have a much better idea of it now. But a very simple question is, how many of these probe packets should I send? A similar sort of sounding question, and actually it's a very closely related question, is how accurate is a particular measurement? And there's another sort of question is, if I want to do this comparison, I told you one of the dangers between these comparisons between, say, network A and network B already, but imagine I want to do this comparison. Imagine I want to compare network A and network B. Would I be able to say network A is better than network B? How many probe measurements would I need to do that? So part of the problem with these questions is they're actually very vague questions. They don't really have enough detail to be meaningful. So what I want to do is firstly tell you what question you need to actually ask. So firstly, the question we're really asking is, if we repeated this measurement under the exact same circumstances, how might the results vary? So what do I mean by that? Well, imagine the network is in a steady state. It's in a nice, well-behaved state that isn't changing over time. What if I'd made the measurements now or in 5 minutes? I wouldn't get exactly the same results, because packet probes, they're always a sample of what's happening. I might lose a packet, I might gain a packet. There's a bit of randomness in it because I'm sampling. So if I repeat the same set of measurements, how much would the results vary? I might measure 1% loss one time and then 1.5% loss another time. And that amount of variation, that's sort of what I would call the accuracy of the measurement. The flip side of that, or the almost dual question, is, given a desired maximum to that variability, how many measurements do I actually need? So these two questions are much better founded questions. We still need a technique to work out how to deal with them. And a very, very common one is to use what are called confidence intervals. Now, confidence intervals are one of those things that are easy to talk about, but statistically there's a lot of little subtleties in them that you have to get right. And I'm going to talk about one of those today. So imagine we have n measurements, big N, and we have little n losses. Then what we're trying to do is estimate a loss probability, and I've indicated the loss probability here by p hat. And p hat, the simple estimate of it is just little n over big N. That's what I put up before. That's something I don't think anyone's going to argue about. The reason this is, at a statistical level, the reason this is the right thing to use for our measurement is that this is what we would call an unbiased estimator of the packet loss. And unbiased just means that its average behavior is correct. The other thing that we should study when we look at an estimator like this, at least part of what we should study, is what we call its variance. And this comes down to one way of estimating what I said, that variability. Imagine we were doing multiple experiments under exactly the same circumstances. How much would they vary? And that's one way of trying to describe that is by this sigma squared. This is my variance of that estimator p hat. Confidence intervals, well, the naive confidence interval, the what I would call IID confidence interval for independent, identically distributed confidence with Gaussian random variables, looks just like this. It's p hat plus or minus z alpha, where z alpha is a parameter that depends on how much confidence I want to have, multiplied by the square root of the variance and divided by the square root of the number of measurements. When we look at 95th percentile confidence intervals, Z alpha is 1.96. So it's very common to just take P hat plus or minus 2 times sigma on root n, and that's your 95th percentile confidence intervals near enough. Okay, so this is what we call the Gaussian confidence interval, assuming that we had IID, independent, identically distributed random variables. Now, I'm sure some of you have come across this before. I've certainly seen some research papers use these when they're talking about loss measurements. The intuition that you would often get from a stats textbook about when this is a valid approach to use is that you have to have NP 1 minus P greater than 10. So what does that mean? Well, imagine that we had a 1% loss rate on our network. So P hat is about 1 in 100. 1 minus P is close to 1, so we ignore that. So we end up with N on 100 should be greater than 10, so N should be about 1,000. So the naive idea of when this approximation, when these confidence intervals are valid, are when you have about 1,000 measurements. That's quite a lot. I mean, if you imagine taking measurements every second, that's 1,000 seconds. That's, up not that far off 20 minutes worth of measurements. So this was my naive answer when I was first asked about this question is, let's try and make sure we have at least an order of 1,000 measurements so that we could measure 1% loss, and then we can estimate the confidence intervals reasonably, and we'll go from there. If you have less than N, then you don't need to give up. Less than this, you don't have to give up. People would say, they'd say use a student T distribution instead of a Gaussian distribution. There's all sorts of statistical theory here. Okay. The problem is, it's all wrong. The problem with this estimate, there are many problems with this estimate. There's at least 4 I can cite today, problems with this technique. I've listed 4 problems there. And when I say wrong, I don't mean the math is wrong. I mean that the assumptions that lead to this formulation are wrong. And the assumptions are all sort of listed here, but the one I'm going to focus on today is this one. These confidence intervals assume that your loss measurements are uncorrelated. But in the internet, losses occur in bursts. What that means, what I mean by saying they occur in bursts, is that loss measurements are correlated. Loss measurements are correlated. And that means that this formula is not right. This formula is actually very badly wrong. How do you actually calculate the variance here? How do you actually do this? Well, what you need to do is look at a thing called the autocovariance. And I put the math up today, but I don't expect to go into any sort of detail on this particular math, except to say that it creates a way forward. So this is not a problem. This is not a thing that means you can't do confidence intervals. It's a problem that says you have to be careful about how you calculate them. And the way forward is you estimate the autocovariance function. And once you have an estimate of that, you can now calculate a new variance here from this formula. And once you calculate that variance, you can now calculate appropriate confidence intervals. So we did that a couple of years ago, and we looked at a couple of example sets of measurements. Let me spend just 2 minutes explaining this picture, because it is a little bit confusing, I think. This is actually based on a set of measurements in a project that was called Queen. And there were measurements of the packet losses at DNS servers. So when I said packet loss, I sort of used the example packet loss across the network, but this is true of server losses or any other sort of loss measurement you care to mention. So these are DNS server measurements. Why did we use this set of data? Well, we wanted to show that this applied to servers as well as networks. we also wanted to reuse other people's data as part of what I believe is a very important thing in network measurement, which is reproducible research. So I don't want to harp on that, but I did want to mention it. So let me explain what's in this picture. Firstly, the way we've arrived at this picture is by a statistical process called cross-validation. Now, the idea of cross-validation is you have two sets of data. You have a data set which you use to train or estimate or do your calculation, and then you have a test data set. And you use the two to compare the quality of your result. In our case, what that means effectively is the red line corresponds to what I would call the true measurement, and the bars here correspond to our performance estimate. Now, we have to do some magic to get that comparison. I don't want to go into all of the details of it. It's written up in a paper, but you can think of the red line as the true value and the blue and the black bars as estimates. Now you can see that I have a point estimate in each of these cases, the little circle or the little square, and then I have a bar around it. The bar is the confidence interval. The two are the black ones and the blue ones. The black ones are sort of pushed to the left just a little bit, and that's just so that we can see them. They actually should all be sitting in the same point, but then it becomes very hard to see what's going on. So imagine that they're all lined up together. Now, the black bars are the bars you would get from this formula I showed you first up. They're the bars, the confidence intervals that you get from this formula for 95% confidence intervals. Now, let me do a very simple experiment. I'm going to look at those black bars and the measurements they correspond to and work out how often my confidence interval overlaps with a true measurement, or rather how often it doesn't overlap. Let's see. That one overlaps. The first one does, second one does, third one doesn't, fourth one doesn't, fifth one doesn't, seventh one doesn't, ninth one does, but only if you realize that it's been displaced, 10th one does, and so on. In actuality, about half of those confidence intervals don't overlap the true value. Now, given these are 95% confidence intervals, that's ridiculous. We should expect, on average, 95% of them would overlap the true measurement. Now, this is statistics, so it's not going to be exactly 95%, but 50% is ridiculous. It's wrong. Those bars, those black bars, are much, much too narrow. The blue bars are the ones we get if we do this. If we actually try and do a proper estimate of the covariance, and from that estimate of the covariance, we estimate a true confidence interval. And now if you look at the blue bars and whether they overlap, you see that there's only one of them from trace 7, which doesn't overlap its true estimate. And that's about right. Again, it's not going to be exactly 95%, not least because we've only got 13 traces here. Okay, so what's the story here? What's the meaning of this? Well, I've already said part of it. Partly those naive confidence intervals, those independent confidence intervals, the independent Gaussian assumption just gives you much, much too narrow a confidence interval. It gives you wrong. They're just wrong. There's no other way of saying it. They're wrong. The real confidence intervals are much wider. And this has really important implications. Firstly, if I'm trying to compare two sets of network measurements, the chance that their confidence intervals will overlap, given these are much wider. So imagine I'm comparing trace 9 and trace 10. Trace 9 and trace 10 look like, from the black confidence intervals, look like one is obviously better than the other. But if I look at the blue confidence intervals, you can see that they overlap. And therefore, we can't statistically discriminate between the two. So that simple sort of implication that trace 9 is better than trace 10 is not supportable by the actual data. What else? Well, I told you to get these confidence intervals to be reasonable into the right sort of ballpark, I needed something like 1,000 measurements. Actually, I need quite a lot more. So a lot of the internet measurement experiments people have done with packet loss just don't have enough measurements to support any really useful conclusion. That sounds crazy. It sounds crazy. It sounds like I'm saying everyone did things badly and all their results are wrong. Unfortunately, that is what I'm saying. There's an awful lot of research out there which I don't believe anymore because of this issue. Just to help you believe that this is not a once-off event, this is a set of data from web server losses, and we've also done active packet measurements across networks and shown the same sort of properties hold. The basic truth is that the degree of confidence you can have in any set of packet loss measurements is much lower than most people think. And I've heard network operators talk about this problem, and they talk about it in weird terms. They talk about microbursts of packet losses, and they talk about the reason their loss measurements missed something because they were too far apart. But it's really a statistical issue, and it's an issue that you can quantify quite nicely. Okay. If you care about this sort of thing, then I recommend you go and have a look at SAIL, which is our little project to try and do this a little bit better. We have MATLAB code to help calculate these confidence intervals. But at the very least, you need to start thinking about the statistics that you're doing and the statistics you're using and how the properties of the underlying data affect them a little bit more carefully. There are many, many other similar statistical issues. I've talked about 3 today. I didn't get into a lot of them, but you know, ultimately statistics is hard. One of the reasons why you can do a university degree in statistics is because there's a lot to learn. So what do we do about it? Well, obviously, I'm being unfair on us as a community. There are actually some people in this community who are wonderful statisticians and wonderful analysts, and I really don't want to overgeneralize here. There's a lot of research going on how to perform measurements better and how analysis comes into that process. And I'm sure some of you are involved in this sort of research. But please do be careful. Now, part of being careful is to learn some statistics. But ultimately, there are some subtleties that even I have missed in the past. And I tried to point out my culpability in this by telling you that I got it wrong at least once in my career. And I've tried to do that because I want you guys to start to think about how you do statistics, not just as something you add on afterwards. For instance, in medical research, now it's very common, for instance, in Australia, if you want to apply for a medical research grant, you have to have a statistician on the team. Your grant application won't be taken seriously unless that you show that you have someone with actual statistical expertise who is going to help you with your, not just your analysis, but also your experimental design. And that's the other thing that I would like to say today is talk to a statistician before you do your measurements. And there's a lovely quote by Ronald Fisher up on the screen. Ronald Fisher is one of the fathers of modern statistics. And he's a particular favorite of mine because he actually spent the last few years of his life in Adelaide. Perhaps a fact not that many people know. Back in the city that I'm in right at this very moment. But he's famous for many things. One of them is this quote, "To consult the statistician after an experiment is finished is often merely to ask him to conduct a post-mortem examination. He can perhaps say what the experiment died of." And that's the thought that I would like to leave you guys with. Sorry about the Stats 101 for those already initiated. I know there's probably people in the audience who know this stuff really well, and I apologize to you for being at the very best patronizing, but I think this is an issue that affects a lot of people in our community. And I'd like to open the floor for questions. But someone will have to come and talk to the microphone.
So are there... Okay, just quick check first. Can you hear us?
Yes, I can hear you. Okay. Yes.
So questions. Okay, Fabio has a question, right? So coming to microphone.
Yep.
So thanks, you made the point very clear that statistics can be insidious even for skilled person, let alone those that don't take it seriously, and this happened much too often in our community. Having said that, raising awareness about the importance, but also about the subtleties of using statistics tools naively is important. I think in some sense also educational event like the PhD school that we had last year might contribute. Probably we should do more in this direction. Having said that, I think one of the problems is that when papers with poorly or dramatically wrong conclusions based on terrific terrible mistakes, statistical mistakes get published on important venues. I mean, they have a long-term damage. They bring a long-term damage under many respects to the students, to the readers, etc. So once that you pollute the knowledge basis that is paper, I mean, this remains. Having said that, don't you think that in addition to try to prevent as much as possible this pollution of erroneous studies, the community should have some way of, let's say, also, limiting the damage of a paper that got published? Maybe not that you cannot implement with drone, but at least some public criticism being attached or tagged to the paper, such that when a student reads this paper, does not automatically, so he can also learn somehow the criticism associated to it that were issued after the publication phase. Because as a student, if I get something published on a major conference, I take it as a Bible ground truth. I will repeat the same methodology. It influences me, and it takes maybe 10 years of maturity to learn how to, to learn that this was actually wrong. If I get to read a paper with some maybe some criticism, some open criticism alongside, maybe I can this can influence me much less, or maybe I will be influenced by the criticism more than of the paper. So can you maybe comment on what we could do in our community in this respect? Thanks.
I really agree with what you're saying, and the point I think you're trying to make, and the point I would make is that people who collect data and then analyze data and write a paper about it, okay, so maybe they do something wrong. That's not the worst thing that could happen. The worst thing that could happen is they keep the data secret and no one can ever look at it or check it or confirm or deny what they've done. And then people who go out and try and do repeated measurements of the same topic, often they find they can't publish their paper because it's seen as incremental or it's seen as just the same sort of thing again. And so I think that the thing that needs to change is not necessarily that program committees have to suddenly do something. It would be terrible if we reject every paper because we felt that the statistics of that paper were not good enough, and so we just started rejecting everything. What we need to do is allow people to firstly see data as often as possible. And sometimes I know you can't make your data public, and I've been in this situation. You can't publish the data, but often you could let the person look at that data under a non-disclosure agreement. And we don't do that very much in this community. For instance, in medical data research, privacy is a huge issue. And it's very common that the original data set can't be made completely public. But there is often an assumption that if you went to those guys and worked under a non-disclosure agreement, you could do some work on that data. So I think that ability to reproduce results, That's something that really would improve the network measurement community. The other side of it, that ability to publish papers which are, in some sense, replication studies of existing work. I think that's really scientifically important. And yet sometimes you get the impression that if you did a replication study, no one would be interested or no one would publish it. And I've sat in CCOM program committee meetings where people have said, oh, well, this is just the same thing that someone else did. We're not going to even take it seriously. And I find that very frustrating. So I would like to see our community be better at that. And I know that in various years, PAM and IMC have had explicit statements about encouraging replication studies. I'd like to see that happen as often as possible.
If I can add something, replication is one part of the problem. Sometimes you find a failure in the paper. You don't need to get the data to understand that this was wrong, right? So some papers have, as you say, maybe but just reading the paper, you can pinpoint a major flaw in the methodology, not even without looking at the data. But the paper stays there.
No, that's absolutely true. And I've been in this situation a couple of times, and I know one case where we found a problem in a paper and we wrote up a description of the problem and sent it back to be published, and no one was interested because it was seen as sort of incremental or replication stuff. And people in our community, sometimes they really want novelty, they want excitement, rather than really solid work. And sometimes I find that frustrating.
Thanks.
More questions? Oh. And? Okay. I also have a question. Since there are here many students, in the courses that master and bachelor students have, they learn often how to apply certain statistic methods, but they don't learn when not to apply them, right? Like the confidence interval.
Yeah, exactly.
So what would be a good starting
sorry.
point? Yeah. Oh, sorry.
What's a good starting point? Well, I certainly think that it's better to know statistics, know basic statistics, than to not know about it. The trouble with most courses, and I include the courses that I've taught for engineers, is that they're often taught as a bunch of formulas. They're taught very formulaic, and the underlying mathematics, the underlying intuition is hidden from the students because it's seen as too hard or too scary or something. I think that's a problem with teaching. I think we can do better with teaching. But at the end of the day, I think the best thing you can do is make friends with a statistician. And they're not scary guys. They're often very interested in working on problems outside of whatever, these days a lot of them work on biostatistics, and they're very interested in finding out other places where their work might apply. And so it's a really worthwhile relationship if you can find someone to work with at that level. So much of research is about relationships. It's something that I never really understood when I was a PhD student. So much of it is about building relationships so that you know the person to go and ask a question.
Sorry, say again?
Does that answer the question?
Yes, it does. Okay.
I have a question to you, because you said consult someone with a solid background in statistical analysis, which sounds logical, but the errors that you earlier gave in the example of losses, that, for example, losses are not, say, random, but they occur in bursts. And you gave some other reasons why the, say, original statements were wrong. would statistical people be able to find that? That's not always my experience, because they love to dive into more complex statistical models, but they don't understand the real problem. And it's not the statistics that is the problem, but it is, say, the assumptions about reality that's the problem.
That's a really good question. That's a fantastic question. Ultimately, you need to know something about the data or the network in order to be able to work out the right thing to do. And this is true in any domain. This is true in medicine. This is true in our domain. Your average statistician, when you walk into his office and say, "Oh, I've got a problem for you," he won't know anything about that. And so any interaction should be a dialogue. It shouldn't be, I turn up at your office one day and say, "I've got this problem, you're a statistician, you can tell me the answer to it." You need to talk about the issues, you need to explain the problem, and you need to tease out solutions to it. And it isn't something that's going to happen in a 1 hour meeting. It's something that will happen over time. And a good statistician, and I know quite a few statisticians these days, a good statistician will be quite good at the idea of taking a data set and teasing out bits of it that are important. And this is, we sometimes think of statistics and mathematics in general as a science. We think of it as if A happens, you do B. But statisticians, really good statisticians, are almost like artists. And their art is taking data and interpreting it. And they have a lot of mathematical tools that help with it, but they also often have a lot of intuition and a surprising degree of flexibility about how they do their analysis. I say a good statistician. I've also met statisticians, the phrase, "If all you have is a hammer, then everything looks like a nail." You sometimes get people, they have their pet technique, and every problem becomes, does my pet technique work on this? And I don't like working with people like that. I would much rather talk to people who are a bit more flexible and think about what your problem is. But again, finding those sort of people, it's about building relationships. And I don't have any trouble believing there are good statisticians all around the world just looking for lots of interesting problems. Is that fair? Does that answer your question?
Yes, it seems so. Okay. Other questions? No? Okay, then thanks again a lot to Matt.